Welcome everyone. First of all, thank you very much CppIndia for giving me this platform to present. It's really a privilege. Uh, and thank you everyone for showing up. I know it's close to lunchtime there, so please bear with me without sleeping. So let's start. So my presentation today is, as Anko mentioned, let's have a solid start. That is, yeah, I'm trying to unleash solid principles before you. A few good housekeeping principles. Uh, Please have your cameras on. Seeing the faces really support a connected discussion. Please have your microphone on mute while you are not speaking. Feel free to ask questions by unmuting or post in the meeting chat. So without any further delay, here is the agenda for my session today. I will cover solid principles, try to cover the solid principles by answering some questions about solid principles, like why solid principles, what are the solid principles, how solid principles is going to help you, who are the creators of solid principles, and when it is introduced, which are the solid principles and what are they. I'll try to explain it using some example code and how those solid principles can be used in your design. As I'm familiar with C++, I'm using C++ code examples, but solid principles is we could say that it is independent of the programming language or the programming paradigm. So it is not only for C++, it could be used in any programming language. All good? Our first first topic, which is why solid principles, or I would say that what are the goals of solid principles. Before that, let me ask you a question. What is a software and how it is differ from hardware? The simple, straightforward answer would be a software is soft, whereas hardware is hard. What I meant by software is soft, it means when it comes to introducing requirement changes in a software, it is easier. Whereas in a hardware, it is hard or difficult to introduce requirement changes once it is produced and out. Back to solid principles. So good software systems begin with clean code. Another question, what do you mean by clean code? Does it mean that code which is written in a well-formatted manner, in a like something fancy? Or let me rephrase in another way. How do you know that a code is bad? Or what are the symptoms of bad code? A bad code is often confusing. It is difficult to understand, whereas a good code is more understandable, or like it is a self-explanatory. So let's come back to some of the symptoms of bad code. There are many, of course, many symptoms of bad code. I will explain 3 symptoms here. First one is rigidity. So what do you mean? What do you mean by rigidity in a software system? Rigidity means a system. When I introduce some changes, requirement changes to a system, it causes a cascade of changes in some other parts of the application. That means in order to introduce a small change to a software application, a cascade, many changes, many dependent changes are to be needed. So that means we say that system is rigid. I mean, the more modules you have to change for introducing a particular requirement change, the more rigid the system is. We all might have faced such situations. Think of a situation when you say, like, you are asked to introduce a feature enhancement in your system, and you estimated the work and mentioned some estimate, and finally you end up saying that uh, it was too much more than I expected. Why? Because when I try to introduce that change, I realized that I have to make modifications in different parts of the applications, and many different changes are to be done to make it final. So that is the first symptom, which is rigidity. The symptoms are, I'm explaining symptoms of bad code. Second symptom, which I'm going to explain, is fragility. Fragile. What is the word meaning of fragile? Fragile meaning easy to break. How? I'm trying to introduce a change to my system, but as a system, this software system is fragile, it causes some other parts of the code to break. Even the system parts which are not directly related to the change which I am making. These scenarios also we might have experienced. Think of a situation when we usually do the bug fix. We do some change to fix a bug and some other parts of the system break. You might have heard like your manager rush to you and telling you, please don't touch that portion of the code. So that is symptom called fragility. Your system design is fragile. And the third symptom, which I'm going to discuss, is immobility. What is the term immobility means? In here, in software aspects, immobility meaning difficult to reuse. That means the system is very difficult to disentangle into components that could be used in other applications. Why? It is because there are many dependencies between these components. So for example, I have a logger component in my application. If I need to use that logger in a different application, if it is tightly coupled, it's very difficult to reuse it in another application. So immobility is also a symptom of bad code. As I mentioned earlier, there are many symptoms of bad code. These are just a few of those. Back to why solid principles. So solid principles are guidelines to clean code. Its goal is the creation of mid-level software structures that tolerate change, are easy to understand, are the basis of components that can be used in many software systems. So what do you mean by mid-level software structures? By mid-level software structures, I mean that solid principles can be applied by programmers working at module level. That means it's not at high-level architecture or high-level design side, software architecture or high-level design. Solid principles can be applicable to the low-level design or just above the code. And solid principles will help you to define your software structures within your modules. Clear? So now that we know about the goal of solid principles, let's define what are the solid principles. What are solid principles? Solid principles are the most important design principles, or they say it is the first 5 design principles in object-oriented design. When I say object-oriented design, is it only object-oriented design? No. Solid principles can be considered as a universal set of design principles. As I mentioned earlier as well, it is applicable to any programming paradigm, be it object-oriented, generic, or functional programming paradigm, or even procedural programming. So I'll state the Wikipedia definition of solid principles here. Wikipedia says solid principles are the 5 design principles intended to make software designs more understandable, flexible, and maintainable. Solid principles also form a core philosophy behind agile software development. Now let's move on to how solid principles help us. So as we mentioned earlier, solid principles tell us how to arrange our functions and data structures into classes and how those classes should be interconnected. Again, the term class here doesn't mean that it is only applicable to classes in object-oriented design. By class, I mean a software entity or a grouping, like a cohesive grouping of functions and data structures. You could see that software entity as a class or a module, or in C programming language, or like in procedure programming, it is even a source file. We are making some groupings, right? So wherever that groupings of some functions and data structures are present, we could apply solid principles there. Now we can see who are the creators of solid principles and a little bit about its origin. History of solid principles is long actually. Originally, solid principles are a subset of many different software design principles promoted by Mr. Robert C. Martin, who is an American software engineer trainer and all, and who is also commonly known as Uncle Bob. He started to assemble such design principles in the early 1980s. Over the time, many of these principles have changed. He added certain principles, he deleted some things, some of the things have been changed. And around 2000, he stabilized a set of principles, presented them in a different manner, different way actually. And in around 2004, Mr. Michael Feathers suggested the idea of rearranging those principles in an order so that the first letters would spell the word solid. And hence, solid principles are born. So without any further delay, I'm going to reveal you the solid principles. They are single responsibility principle, open-close principle, Lisco substitution principle, interface segregation principle, and dependency inversion principle. See, the first letters of all these words forms the word solid. First is the single responsibility principle, or in short term, SRP. The key term behind single responsibility principle is high cohesion. I will explain what is cohesion in a couple of minutes. So single responsibility principle states that a module should have one and only one reason to change. This is a principle stated by Robert C. Martin himself. To explain a bit, single responsibility principle is actually one of the most or least well understood principle in the solid principles. Why? Because it is like from the term single responsibility, people might assume that a module should have only one functionality, or module should do only one functionality. But that is really not the case of single responsibility principle. Even if you see that, like, we have, like, while writing functions, we to make the function small, we practice a rule, like each functions should do only one thing. But Robert C. Martin mentions that is not SRP principle. Yeah, that is another thing. But that can't be mapped to a single responsibility principle, because, like, single responsibility principle is applicable in the low level design and module way, not in this. The other rule is not single responsibility principle. So here we are considering a module should have one and only one reason to change. Again, here the module could be is a software entity, could be a class, struct, or any grouping of functions and data structures, could be a source file as well. So, so such grouping, how such grouping is has come? It is a cohesive grouping of functions and data structures. So now we can move to what do you mean by cohesion? So Tom DeMarco, in his paper Structured Analysis and System Specification, he mentions about cohesion. I'll read it out. Cohesion is a measure of the strength of association of the elements inside a module. A highly cohesive module is a collection of statements and data items that should be treated as a whole because they are so closely related. Any attempt to divide them up would only result in increased coupling and decreased readability. So that is what cohesion meaning. So that means functionalities that are semantically or logically connected to one particular module will belong in that module. Functionalities that is not logically connected would be divided up into different modules. So now we can connect about high cohesion, which I mentioned in during the start of solid SRP principle. Like the key term behind SRP is high cohesion. What I mean is like in like how that is related to SRP is like by making the modules cohesive, we are actually reducing the number of reasons to change that module. I mean, yeah, that's it. By making the module cohesive, we are actually relying or conforming to single responsibility principle by having only one reason to change for a particular for that module. I'll explain with an example. You will be clear after the example. First, we see a violation example. Single responsibility principle violation. If you see the code, here is a photo uploader class. From the name, we can understand that it is something that is handling uploading of images, possibly to a cloud. This class has three public methods: retrieve image, resize image, and upload image. We can see let's think of what are the possibilities of change for this module. So we can clearly see that there are different changes, the different reasons for change for this module. So photo uploader class is dependent on the camera class and cloud provider class. So what are the different changes? So if camera class changes, for example, if the way how the camera we use got changed, this photo uploader class need to be changed. The changes could be in the source code change or even the with respect to the binary buildings. So I will be definitely including a header file over here. So if I change the camera's header file, my source code, photo uploader source code also need to be rebuilt. So that's also a change. Similarly, if the cloud provider, something happens to the cloud provider class. So for example, I am changing my cloud provider from one to another. I'm choosing a different cloud provider. That's also a reason for photo uploader class to change. And when the image changes, I mean, image class changes meaning suppose attributes of an image change. So as we have resize image functionality over here, if attributes of image change, that may affect that resize image functionality as well. And original, then the fourth reason for change is the core functionality. Any change happens in the core functionality, like upload image. If there is a logic change expected in the upload image or requirement change happens in the upload image, then also we need to change this photo uploader class. We can clearly say that this photo uploader design is violating single responsibility principle. Why? Because this module has different reasons for change. Now let's see a better way. See here. So now I have make this module short. I have taken out the camera class, dependency with the camera class from here, because I don't think that semantically belong to photo uploader class. So camera, you could see that the get image and resize image, those functionalities are not all as well not related here. Like it could go into different, it could be divided into different class. Resize image is anyway belonging is a functionality which is cohesive, which could belong in the image class. So this function will go there. Get image is also not required actually. So I will finally come up with a photo uploader which is depending only on the cloud provider, and the upload image also becomes like with this public method upload image, the client classes of this class can pass the image that is to be uploaded, and that would be uploaded to the selected cloud provider. So thus I try to make this class the reason for changing this class to minimum. I'm not telling this is a hard and fast rule. So here the thing which you have to think about, or like when you think about single responsibility principle, we have to think about the number of dependencies for a particular module and keep the dependencies to minimum while keeping the module as cohesive as possible. Single responsibility principle. Here are more examples of single responsibility principle. The best examples are STL, design of STL, or the standard template library. You can see that the data structures, algorithms, containers, everything in STL is nicely following single responsibility principle, and these are very well separated. What do you mean by that? A change in one of the container is not affecting any other containers. Of course, they share some interfaces, common interfaces like iterator. There are many containers which are iterable containers, right? So that iterators is a common interface that is being shared across, but still we can the basic STL is being basic SRP principle is being confirmed to in STL design. There are exceptions, of course. For example, STL vector is nicely following single responsibility principle, whereas STL string class, string library is not following single responsibility principle. I mean, the implementation behind the STL vector and STL string. STL vector follows single responsibility principle, whereas STL string does not follow single responsibility principle. So finally, here is a takeaway from this explanation about single responsibility principle. Single responsibility principle is one of the simplest of the principles, but it is one of the hardest to get it right. Prefer cohesive software entities. Cohesion, high cohesion. Everything that does not strictly belong together should be separated. So prefer always cohesive software entities and make dependencies to the minimum so that there are minimal reasons to change, or like single responsibility principle says, a module should have only one reason to change. So now that we covered the first principle in our solid principles, I'll move on to the second point, second principle, which is open close principle. Open close principle is OCP. So key terminology here is simplifying addition or extension of functionality. Open close principle is coined by Mr. Bertrand Meyer in the year 1988, and open close principle states like this. A software artifact should be open for extension but closed for modification. What do you mean by software artifact? Again, it is a module or class, anything like that. So what do you mean by open for extension and closed for modification? So anytime the software can be changed to extend its functionality without touching the existing code. So new code can be written without touching old code. I'll show you with an example. First, we see, as in the SRP, we see the violation example, and then we'll see our better approach. So here, the well-known shape example in a procedural approach. So you have a shape.h file. We have a shape class, and shape class has a member, an enum type, and enum type enum type could be either circle or square, because we have two shapes currently, and the square and circle are derived classes from shape. As we are only considering the drawing part, square and circle has like parameters needed for drawing, not parameters, data members needed for drawing those shapes. So each of which also holds the enum type, shape type, and it would be square for square class and circle for circle class. Square will have data members its side and top left, because we need that for drawing it, and circle is having radius and center. You can see that the draw square and draw circle functions are now free methods, free functions, which is outside of the class. Draw square takes a square pointer, and circle function takes a circle pointer. And we have another file called drawshapes.cpp, which has a function draw all shapes, which accepts a list of shape pointers and the number of shapes. It iterates through the list, and depending on the type, it draws square or draws circle. So we can clearly see that it violates open close principle. So if I want to add a new shape into this program, I have to one change I have to do is I have to implement a new class, for example triangle, new triangle class. But the main problem is I have to touch this old code to implement that feature. Why? Because the type we are storing in an enum. So we have to modify the switch statement and handle it accordingly. So this is a simple example. So we feel like, yeah, only light modifications are required. But suppose in a real world example, there may be functions not only for draw, we'll have functions for moving, functions for dragging, resizing, and these changes may be scattered across application. So what does that mean? In order to introduce a change or introduce a new shape to this program, I have to search for all the places where I have the switch statement or if else loop, and I have to modify everywhere. So that means we are touching or modifying old code a lot, and thus it violates the open close principle for when it comes to addition of a new shape here. Clear? So now we can see a better approach for example, in the object-oriented way. It's a familiar program anyway. So what happens in this when we refactor in this way? So we have the class shape. There is no enum type anymore. The draw function is now a virtual function. So we have the square class and the circle class, and we are overriding the draw method in the square class and the circle class. How our draw shapes will it becomes a little more lighter. Again, we have the list of pointers. I'm iterating to the list and I'm calling the draw method. As it is a base class pointer, because of the polymorphism, with the same pointer, I can call the draw method. Depending on the type of the pointer, it will call the corresponding square or circle draw. So when we like, how does it conform to open close principle now? When I'm trying to add a new triangle class, what is the change I require? I have to create a new class here, class triangle, but I'm not changing any of these files. I'm not even touching any line in this file because I don't have to, because it is there is nothing new addition I have to do for supporting a triangle here. Okay, and thus this design conforms to open close principle with respect to addition of new types. Here is a food for thought for you. Do you think the object-oriented approach can handle any type of requirement change conforming to OCP? Any thoughts? Suppose the customer requirement is like that. I have to draw all the circles first and then draw all other shapes. Believe me, customer requirements can come in any way. We can't expect what is a requirement change they need, right? So that is also a requirement change. In that case, do you believe that this will conform to open close principle? Because we need in that case, we need a condition check. Like if I need to draw all circles followed by other shapes, I need to understand what is the type over here. So I need to change the existing code. So does that mean we are breaking we are breaking the functionality as a whole? So what is a key point which we need to remember from this? The key point is that like we can't expect the likelihood of the requirement change. So we need to actually think of likely requirement changes that can come, and we need to abstract areas that are likely to be changed frequently. Okay, so here is an exercise for you. Think of how we can handle this like the requirement change which I just mentioned for drawing circles followed by followed by other shapes conforming to OCP. That's an exercise for you for this weekend. Just think of. And if you are really interested, refer Agile Software Development Principles, Patterns, and Practices book by Robert C. Martin in his OCP. Under the section OCP, he's dealing with such a case. So it's an interesting read. So what is a hard truth about OCP? In general, no matter how closed a module is, there is always be some kind of change against which it is not closed. There is no model that is natural to all contexts. Since closure cannot be complete, it must be strategic. That's the key point there. So software designers should think of or should make educated guesses about the likely changes that we can expect in a particular module. And if particular area is expecting frequent changes, we have to create proper abstractions to make it immune or tolerate to changes. No design is completely can be made completely closer to every requirement change that can be expected. So conforming to OCP is actually an expensive process. Why? It needs a lot of thinking, lot of effort to make this proper abstractions, and also it needs some experience like that. So here is the takeaway. Prefer software design that allows addition of types or operations without the need to modify existing code. Open close principle is actually a heart of object-oriented design, which enables object-oriented it conformance to OCP actually yields the greatest benefits claimed for object-oriented branding, like flexibility, maintainability, reusability. So OCP is accomplished by identifying and applying abstraction only to those parts of the program that exhibit frequent change. That is a key point there. We can't make abstractions, or like we can't make abstraction throughout the code. That also makes the code difficult to understand, or like it impacts the readability of the code. We should identify places that are prone to frequent changes and then make abstractions appropriately. That is what OCP suggests us to do. We are moving to our third principle, Lisco Substitution Principle, or LSP. Lisco Substitution Principle, the key term is substitutability. Barbara Lisco, a mathematician, in 1988 states Lisco substitution principle like this. I'll read it out. If for each object O1 of type S, then there is an object O2 of type T such that for all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2. Then S is a subtype of T. Oh, bad. Luckily, we have in simple words we can tell that Lisco substitution principle states subtypes must be substitutable for their base types. So it's all about substitution or inheritance hierarchies. So it's all about behavioral subtyping. What do you mean by behavioral subtyping? You might have heard of the term is-say relationship, right? When you think about the inheritance hierarchies, for example, in examples we say like car is a vehicle, or something sparrow is a bird. So these is-say where we are trying to substitute derived type with a base type, derived types with a base type. In all those scenarios, Lisco substitution principles apply. As in the other principles, I will first show you a violation, and then we see how the code can be bettered. So here is the classic square rectangle dilemma. So here is a rectangle class, class rectangle. It has private members, top left, width and height. And the public methods, set width, set height, get height and get width. So I need a square. So mathematically we can tell that square is a type of rectangle having equal sides. So the designer of this program think that yeah, square can be derived from a rectangle, and he might have thought like we could make some tweaks in the rectangle in our base type, and we can reuse it. So the square class come like this. Class square derived from rectangle. We have set width and set height, but we are making some tweaks. In set width, if I get a width, I will pass the same width to set width and set height. Similarly, I am calling rectangle set width function, rectangle set height function with the same width. Similarly, in the set height, I am calling rectangle set height and set width with the height parameter, so that all the four sides are equal. So what happens? Like if you think of a draw shape, something like the what we seen in the earlier example. If I pass the rectangle pointer to if the draw shape is having the rectangle pointer, I can easily with this change also I can easily pass a square over there. because square is currently derived from rectangle, and it works functionally. It works. But do you think a problem over here? I can show you a problem. So a second person is coming and he is writing a function like this, and he is expecting a pointer over here, a rectangle base pointer type, and setting a width and setting a. He's trying to test this function. So set width 5, set height 4. If we haven't seen the original implementation, he expects that area is 5 into 4, which is 20. So that means if I pass a square over here, this assertion will happen. So do you believe that inheritance is broken? No. But what actually happens is we don't consider the semantics of this program. Mathematically, we can say that a rectangle, so square is a special type of rectangle with all sides equal. But in computer science terminology, when we choose inheritance, we have to think about some more things. Like we have to think about the expectations of the base class, expectations of the interfaces in the base class. So that means we have to think semantically as well. That's what they call behavioral subtyping. So what is the conclusion from here? Here we as the rectangle base class expectations are not met, we can derive square from rectangle because they are two different entities, because they have different expectations. So we can't, with these interfaces, we can't derive a square from a rectangle. Here is another example about templates, which is also an example for Lisco substitution principle. Mr. Klaus Ugelberger mentions in the CppIndia his session, breaking dependencies to solid principles. He mentions examples about a template. So here is a naive implementation of std copy algorithm. I can go over. So it is a template function which is which has two iterators. Input, there will be an input iterator as well as an output iterator, and we have 3 parameters over here. So this is a copy, right? So I have an iterable type, first and last pointer, and then a destination. So I'm iterating through this. I have the first and last. So while first not equal to last, I'm iterating and incrementing the first and destination pointer, and each of these values are being copied. Once this iteration is finished, I'll return the destination. That's how the copy works. So how Lisco substitution principle applies to here? So what is the expectation of copy, std copy over here? You can definitely see that it expects iterable types, right? It needs some types that has increment operator as well as comparison operator. Any other types if we pass here, it does not meet that expectation. So that can't be that can't become substitutable over here. So here is a takeaway. Lisco substitution principle is all about substitutability. The term essay is too broad to act as a definition of subtype. So as we mentioned, essay, we simply say essay as a subtype, but we should also consider expectations or semantics of that base type to before we derive something out of a base class. The fourth principle in solid principles is interface segregation principle. The key term behind interface segregation principle is low coupling. I'll get into that. So Robert C. Martin, he states interface segregation principle as clients should not be forced to depend on methods that they do not use. We'll see in the example. So interface segregation principle, we can say that it's a special type of single responsibility principle. So here it deals with disadvantages of fat interfaces. So let's see an example, violation first. So there is a class bird, which is a base class, and I have 4 interfaces here: fly, eat, run, tweet. I'm deriving birds, sparrow, and penguin. So sparrow, it's fine. I can have overridden methods for fly, eat, run, tweet. But how about penguin? Penguin is a bird who can't fly. It has but as we have an interface over here, we are forced to implement fly for penguin. So it is because the bird has a fat interface. That's the reason a bird which is not like semantically it can't fly, but we are forced to override here. So how can we avoid this situation? A better alternative could be, I am, as a principle states, I'm segregating the interfaces into small groupings. So I have a class life form. In that we have methods eat and move. I have a class flyable. In that I have a fly, and I have a audible. In that I have a virtual method make sound. So when it comes to deriving, so class sparrow. So now the design is more flexible. I can have a flexible grouping. I can group these interfaces semantically, so that I don't want to force a client to override something that is not semantically correct for them. So class sparrow can be derived from life form, flyable, audible. But penguin, as it is not flyable, it can derive from life form and audible. And I don't want to override fly in penguin. So this means like I have segregated my interfaces, and I'm giving option to my client to use only the interface which it correctly requires. So here is a takeaway for interface segregation principle. Make sure interfaces are not bloated with member functions that subclasses are unable to implement in a meaningful way. Make sure interfaces don't induce unnecessary dependencies. If that is the case, we are going to the last principle in solid principles, which is dependency inversion principle, or DIP. The key term here is loose coupling. So here is a dependency inversion principle. This is the principle by Robert C. Martin. High-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. We'll see with an example. First, a violation. Suppose there is a class button and a class lamp. So use case here is something kind of a security application. If some people, if a person enters a room, if there is a motion detected over there, light should be turned on. If nobody is in the room, light should be turned off. Like that. So button class has a lamp member over here, and it has a poll method. This poll method could be triggered from anywhere. Maybe it is a invoked from a mobile application or UI, anything like that. So what does this poll function do is poll will sense depending upon the environment sensing, the poll method is called. If some condition is true over there, it will turn on. That means, like, if the poll, suppose in the security example, home security system example, if somebody enters, if a motion is detected, this poll would be inverted. inside this pole, it will check like if it is instructed to turn on. I mean, like if the switch is already on, it will illuminate that room. And if the person went out, the pole is again invoked, and it could be to turn off the lamp. So how, like we'll explain how this is not, this is violating to dependency inversion principle. Now we can see in the diagram, you could see that a button is clearly dependent on the lamp over here. As the arrow is moving towards here, you can also see that button has a lamp member over here. So it is button is clearly dependent on lamp. So as the principle says, like high level modules should not depend on low level modules. Here actually this module is depending on this thing. So it is clearly violating the dependency inversion principle. So how we can make it better? This would be a better approach. Here the dependency inversion is applied. So as you can see here, the arrow was moving out and was like directing to the lamp. So if you see here, dependency is inverted here. How from the lamp it is going out. The button from the button it is still going out, but it's not directly going out to the lamp. We have introduced an abstraction over here. That means like anything that can that can manipulate a lamp, that can be provided as a button server. So we have an abstraction over here. So the button will only interact with the button server, and button server is inherited by lamp, and we are not tightly coupled. Like the button is not tightly coupled to lamp now. What is the advantage of this design? I would say, like, what if I need to control a motor over here? For in the other code, I have many like it is tightly coupled, it will be difficult. But here I can introduce a motor class over here. It is also inheriting from the button server, so it is easier. What if this button is being replaced? For example, now the polling comes, the poll comes from a web server or anything like that. We are directly from a web application, it is controlling. So this side is also independent. We can remove even this side. So now both the sides, the client side and the server side, is independently changed because we have introduced an abstraction over here. And the high level module and the low level module is depending on the abstraction. And the high level module is no more depending on the low level module. And hence, this is a better approach, considering the great deal of flexibility which it provides. You can even think of having this system to support a device that is not even invented right now. 10 years later, this code, I'm going to control a different device. That also is possible. So that's it about dependency inversion principle. What's the takeaway behind it? So dependency inversion principle is the hallmark of good object-oriented design is dependency inversion. No matter what language a program is written, if its dependencies are inverted, it has an object-oriented design. If its dependencies are not inverted, it has a procedural design. Prefer to depend on abstractions instead of concrete types. So that's all about dependency inversion principle.
Yeah, I have a question here.
Yeah, sure.
What is the distinction between Lisco substitution principle and interface segregation? Because both of them kind of doing the same thing.
There is difference. Lisco substitution principle is actually about the substitutability. It is like here we are not like how would I say? We have a scenario where we thought thing like inheritance can be suitable, but when we think of inheritance, we have like, we can't like, if we see some data members common to, like we usually think only in that way, right? If we have data members, some data members common, and we can like here rectangle itself, our mindset was yeah, we have a height and width, we have draw public methods also to set and get and drawing, so we could reuse that. So it is the, here the point is Lisco substitution principle is all about substitutability, and it is not about data, but it is about behavior. It is like when you think of inheritance, when you think of deriving subclasses from a base class, there this Lisco substitution principle is applicable. It is not anything about like, it is about expectations in that interfaces, but we are not telling about segregating or anything like that. Here, if Lisco substitution principle, if you are conforming to Lisco substitution principle, you can use inheritance or not. That's it. Whereas in interface segregation principle, it is kind of when there is a suppose application UI, if such a scenario, application to UI, and if UI is providing a fat interface for from application to send everything, like suppose you think of a desktop application with many different tabs, menu tab or a graph or like data display tab, logging tab, everything. So if I am using a GUI which has only one module which serves as an interface, GUI interface, and from application I have a all these are in a particular in only one file, it is providing a fat interface here. So for example, in employee form filling, for form fill, like if in application, if there are different modules, employee form filling, if there is a window like employee form filling, and if there is a window like employee salary. So if I provide everything as a single interface, it is like modules which doesn't need to be dependent on a particular or doesn't need to know about that, that is also being exposed. So what interface segregation principle suggests is that clients should not be forced to depend on methods that they do not use. That's it. So that would become, we are segregating the interface into small groups, and the client, if it does not need to depend on that, shouldn't need to. That's it.
Yeah, I need to absorb this information. Okay, but I think yeah.
Do you need one more explanation? I can. Is that clear to you?
Yeah. The other day I went through some example and I kind of got confused. Like both of them are doing the similar thing. In the sense like if I say a class should be replaceable or substitutable by its subtypes, that we by this statement we mean like a method which is there in the base class, that should be, that method can also be called by the derived class. By this we mean this, and the similar thing we are meaning in a segregation principle, wherein we are telling the user of the class that we should not be passing on the methods which should not be which should not that should not be dependent, or the derived class should not forced to write that method. So in both the things I am confused, like we are kind of doing the same thing. So yeah.
I wouldn't say it is the same thing, because
Yeah.
like here, suppose the output of Lisco substitution principle, it's an yes or no. If it is, it could be direct, if that could be a subtype. Like when we consider inheritance, if it is a subtype, correct, behaviorally subtype or not. But here, like if you see the bird example as well, sparrow and penguin are birds itself. Semantically, they are correct. But only thing that like there is some behavior which is not which can't be provided by Penguin. So we are making it a small interfaces, and we are combining it. We are flexibly combining this. But this situation is not there. There it is, like Lisco substitution principle. I believe that it is a decision maker for inheritance, whether this could be subtyped or not. But here it is not that. It is the term itself mentioned that is interface segregation. So we are avoiding fat interface by segregating into small things.
Okay.
Does that make sense?
Yeah, sure.
Yeah, like solid principles, we are different. Like I also had to refer a lot because like different, even the single responsibility principle, as I mentioned earlier, like many texts says different ways, but as we know that we can rely on Uncle Bob because he is the one who introduced this in, right? So I refer, like if you see in net single responsibility principle, the same confusion which he says, like there are explanations like a module should implement only one responsibility, but it's not not that single responsibility principle. So some examples are confusing, but I would suggest referring Uncle Bob's books or materials if we have a confusion like that. Does that make sense?
Honey, just to can I add an example here?
Yeah.
Just
Sure,
to drive
sure.
the point. So you have an employee management system where employee can be the CEO of the company, can be a finance guy, can be a petty developer like us. I don't know about you, but you would have functionality to disburse salary, being a finance person, a finance department employee. You would have the responsibility to maintain the code, being being an employee in R&D or whatever on the software side. You will have balance sheet and responsibility of the company profitability as a CEO. So you might have many of these functions. You can think of creating an employee class, at least a base class, which can have all of these functionality, and then every employee has to implement it. But there are employees which will not have one aspect or the other. So it is better to have 3 base classes. One is a finance guy, one is a CEO guy, one is a developer, and one is a manager. So you can choose to implement which functionality, which aspect, which type would follow and implement, and not have to force to have a function like disburse salary if we are in the technical side, and it makes no sense to force this interface on us. That's what the ISP, interface segregation, would say. Separate these different concerns. You can think it is all about an employee, but no, you can see all of these as many different aspects and not overlapping with each other exactly. So you can make them interfaces and then implement in some types which follow. Not all. You may have a type which follows all of these interfaces, but it is not necessary that all of those have to be followed for you to be a finance guy. Everything has to be followed for you to be a software developer. So you can choose to implement some of these. So that's the way to look at ISP. And the Lisco substitution principle says if you have it in the base class, every subclass should follow the invariance, the behavior that the base class intends to. So if you have a disburse salary, you better disburse salary even if you are in R&D. Okay, so you must do it. So don't confuse these two things, and you must do the same operation, and you must leave the state, etc., as expected by any base operation. So every derived class should just follow those things. So that's the LSP.
Thank
Okay,
you, good.
Thanks.
Sorry, went a bit longer than I thought I would.
No worries, no worries. I like I have a point there is like that, like the example which you mentioned, that like if a similarity which we find, it would be a similarity to single responsibility principle as well, right? When we are as Ankur mentioned about that finance manager, all these, like we are also cutting down the number of reasons for the change as well when we segregate it, correct?
Yes.
Yeah.
Segregation does give you SRP also.
Yeah.
Sure.
That's it. Yeah. This is a recap. Thank you for bearing with me. So these are the principles we discussed. First, we have an intro of the solid principles, and we discuss about each of the solid principles. S for single responsibility principle, O for open close principle, L for Lisco substitution principle, I for interface segregation principle, and D for dependency inversion principle. So this is what we learned during the session. And on to the summary. Solid principles enable agile software development. Solid principles are not just a set of object-oriented guidelines. They are a universal set of design principles and a very important design principles as well. Use solid principles to reduce coupling and facilitate change. Thank you very much for listening.